Happy to introduce Surbhi Goel. She's an assistant professor at the University of Pennsylvania, has done really foundational work on understanding when we can actually learn neural networks in polynomial time. And recently has been thinking a lot about how transformers work, trying to understand learning dynamics and generalization, different aspects. And so she'll be telling us today about how to handle adversarial data by abstaining. So let's give her a round of applause.
Thank you so much for the warm introduction and for the invitation to talk here. I'm not going to talk about anything that Spencer mentioned that I work on. So this is something else that I'm interested in, and it's going to be more of a very learning theoretic talk with connections to LLMs being very far-fetched. But it's going to be about this paradigm of trying to handle adversarial data by, instead of not predicting on it, by abstaining and knowing when you should be abstaining when you're tasked with very hard data instances. And the premise that I'm going to take is going to be not supervised learning, but more sequential decision making, because I think like a lot of decision making that our machine learning models are making today is more sequential in nature. And this can go from classical examples that we've seen as spam detection to more real world recent examples, like where ML systems are used to give medical diagnosis of an entire population one at a time, or recommender systems, or now more recently chatbots that have been interacting over many iterations. And one thing that becomes challenging when you're interacting in these online settings is that when test and train data don't look the same, a lot of crazy things happen. We've all seen articles of car crashes by these ML models when they see something that they're not used to in their training data, or these systems in medical diagnosis being not as good or more prone to errors and racial biases than general humans are. And one example that I find pretty interesting, and just a funny example, is this one that I read in New York Times, which is about Apple Watches calling 911. And the only reason they were calling this was somehow they found this correlation that somehow when you're skiing, your heart rate behaves such that it's very similar to when you get heart attacks. So it started calling 911 to ski resorts, and that cost a lot of money because there was a lot of 911 calls that ambulances had to reach. So basically, the challenge here is that when you are not dealing with the same test distribution as the training distribution that you train on, and you have these adversarial or maybe even out of distribution data, these errors that you make on their predictions can be very costly if you're using them to make some decisions downstream. And generally, you could take a theoretic point of view and try to construct these two different worlds to understand these kind of sequences. So one, you can think of this idealized world of stochastic sequences, where you can assume that the data is like really nicely drawn from some fixed IID distribution. You don't know this distribution, but the data is always IID from this distribution. So there's not any correlations across the sequences. And you can take this completely extremely opposite view, that you don't assume anything about the world, and you say that it's completely worst case, that the data is actually generated by some adversary that's deciding at every time, based on what you've done before, what your algorithm you're implementing, what to give you. And it's, as you would imagine, that this is a very benign assumption, and this is a very strong assumption. So it's easy to get guarantees, like really strong guarantees in the first case. And this is too pessimistic to get anything that's reasonable. But on the other hand, of course, this is too simplistic to model the real world. And this, even though this is very robust to changes and attacks, this is also like a very worst case view of the world. And we believe like the real world is not so worst case, but somewhere in the middle of the two extremes, but we really don't know where it lies. And we don't really actually have any control on how much the adversary is going to corrupt. So we kind of want to understand how we can extrapolate between these two settings in a nice way. So the goal of this talk will be to try to understand how we can still achieve these nice, strong guarantees, while in some sense handle any amount of adversarial and outer distribution data. And I'll mention what handling really means. I mean, in the worst case, you can't expect to predict correctly on all adversarial data. So the key idea, potential fix, now you can argue that this is not a fix, would be that we'd allow the model to sometimes just abstain on making a prediction. It can just decide, okay, I'm going to throw my hands up, and I'm not going to make any prediction on this example. And the caveat here is that as long as this model is abstaining on adversarial or out of distribution data, which is this danger area, I'm not going to like really punish the model for doing that. And here you can imagine that if you were running this in a real system, if the model abstains, you can get some human in the loop. Of course, this would be really expensive, but it could label the unsure examples. For example, if an ML system is in a doctor-patient setup, you can call for the doctor for his expertise to look at that example, or when it's in self-driving cars, you can give the control to the human driver when you encounter such a thing. And so today I'm going to describe a framework that tries to incorporate this abstention into the sequential prediction task, and then algorithms that are actually able to achieve strong guarantees while being robust to any amount of adversarial data. And this is joint work with some amazing collaborators, Steve Haneke, Shaimaran, and Abhishek Shetty. Abhishek is here this semester, so if you find this interesting, you should talk to him. He's still thinking about a lot of problems in this space, and this is the paper if you want to take a photo of this. Okay, so this is what I'm going to talk about. First, I'm going to describe the model, and feel free to ask any questions when I'm describing the model. It's important that we understand and agree on the model. And after I describe the model, I will describe the algorithms. And two sets of acknowledgements here. So originally, when I started thinking about this model, this came out of discussions with Theodoros and Adam while I was at MSR. But then eventually, we ended up working with different people on this model. And this builds on this really cool paper by many people here, Shafi Golwasser, Adam Kalai, Yael Karai, and Omar Montasar. I will discuss exactly the connections after, but this is a really cool paper if you want to check this out. Okay, so what is sequential prediction? I'm going to take a very simplified setting. I'm just going to assume it's like a binary prediction task. And there is a true binary function from which the data is coming. So there's no noise. It's like the realizable setting. What's happening at every time instance, there's some data drawn, xi. The learning algorithm gets the data. The learning algorithm makes a prediction. Then it gets to see the true label. It can decide what to update on based on this true label. And then it goes to the next stage, gets another data, makes the same prediction, so forth for capital T rounds. And the goal is here to minimize regret or error, which means that the total number of mistakes that the algorithm makes across the T time. And the way that you want to measure this is that as T goes to infinity, you want the average number of mistakes to go down to 0. So you want to eventually not be making too many mistakes as the sequence grows larger. So now you can imagine a model on how this data is generated. So the one that I showed you on the world, the really nice benign world, is that the data is just, at each iteration, is just drawn from some IID distribution. And if the data is purely stochastic, then this regret depends on this quantity known as VC dimension of the function class. And this you can think of as the complexity notion for offline learning. So even if you got this data offline, you would have to pay this VC dimension like guarantees. Now you could assume the fully adversarial model, where each time the data, there's an adversary that's deciding what data to generate. And if the data is fully adversarial, then this regret actually depends on this notion called little stone dimension. I'm not going to go into defining what this little stone dimension is, but even for classes that have VC dimension 1, little stone dimension can be infinite. So you could absolutely get no guarantees in this worst case situation, and I'll show you an example later where it'll be clear why it's infinite. So this is just to say that it's infinite even when VC dimension learning in the offline setting could be possible. So now I'm going to assume this model in the middle of the two. So what is this model going to look like? At every time sense, there's some distribution, some pure distribution that exists. That's going to be the underlying distribution D. At each time, the adversary can decide whether the adversary wants to corrupt that round or not. Okay? So if the adversary decides to corrupt that round, it can inject an adversarial example. It can be any example outside of this distribution, within this distribution, whatever that adversary wants to do. But the label still, the labeling system is still clean. Like the label will still be correct when you actually predict what label you get. So the adversary does not get to control the label, only decide whether it can inject an example or not. So it can give you, it can challenge the ML model that I'll just give you an adversarial example here, but the actual labeling, like whether that adversarial example is a dog or a cat, doesn't change. Okay, so this sequence is generally stochastic. And once in a while, wherever the adversary can decide to inject an example, and the adversary can do this as many times as the adversary wants. Once I'm not controlling that there's a bound on how much the adversary can inject. Yeah.
Class of labels.
Yeah. Okay. So you can think that your actual task hasn't changed, but the data can be like out of distribution or something like putting mass on like some small point, which would not actually change the underlying task. Really, yeah. And this is really important that the adversary does not get to see what the clean input would have been, because then there's no notion of what the IID data is and what the non-IID data is. So in one sense, if I removed all the adversarial points, the rest of the remaining stream is IID.
Is it a realizable
Setting or not necessarily?
Realizable, I mean, for all the results that we have, but you could obviously ask this question in the non-realizable setting. You could handle like some benign noise. I'm not sure if the adversary was allowed to corrupt the label, it would become really, really challenging. Okay, and the other thing with abstention is now instead of predicting just like 0 or 1, I'm going to allow the learner to decide to abstain on some points. Now you can ask whether when it abstains, does it actually get the true label or not? There'll be different settings. Of course, if you don't get the true label, sometimes it can be really challenging. Sometimes you can handle when the adversary, when the learner does not get the label when it abstains. Yeah. No. No, the adversary does not have a budget. I'll explain. The guarantees will change. What kind of guarantees you can hope for. Okay, so the learner gets this extra option. So it's like 0, 1, and abstain. So don't read this. It's just like trying to write the sequential model. Just to know that like the adversary can choose that initial distribution if the adversary wants, and the function that is actually labeling the model. And then the adversary decides at each round whether to inject an adversarial input or not. And you always receive a clean label. That's important. You may not always receive the label, but it's going to be clean when you get it. Then assume a realizable model. There's a fixed f star at the start. You could imagine that you could adaptively change f star to, as long as it's consistent with everything that's seen before. We can sometimes handle that, not always. And it's insertion only, which means the adversarial examples are inserted before seeing the IID examples. And now you can obviously ask this is same as stochastic if there were no adversarial injections, and it is same as fully adversarial if all examples were injected. So right now I've not said anything. This is just capturing the entire spectrum of the two. Okay, so what are we going to try to optimize? So we're going to change our goal. That we're not going to expect it to be predicting on everything correctly, because if it was doing that, then we would have the same guarantees as like the fully worst case setup. So what we're going to try to do is two things. We would try to make sure that we minimize incorrect predictions. So that whenever the learner does decide to predict, it should have low error. Okay? So this is going to be incorrect prediction. That's just the part of the regret. But the other thing that we want, because a trivial algorithm could just abstain on everything, then it's going to have no prediction. So we'll also make sure that incorrect abstentions are penalized. So whenever the learner abstains on non-adversarial data, the rounds that were not corrupted, it's going to get a loss of 1, 2. So now here, if you think about it, these errors are like can be broken down into this misclassification error, which is like all the errors that you're making when you're making a prediction, and the abstention error. But the abstention error is not on all possible points. Technically, abstentions on adversarial examples are actually free. So in this model, I'm not penalizing if you're abstaining correctly on a point that is adversarial outer distribution. Yeah.
Does adversary have access to the nature's distribution?
We'll talk about settings when it has and when it does not have, but it does not get to see whether the point was corrupted or not. So it doesn't know that whether that point that it saw when the learner was predicting, that it doesn't know that the past points, which ones were ID, which ones were not ID. So it doesn't have that.
The thing I'm trying to understand is, like if adversary produces an X hat, which is kind of very similar to what would have been drawn from the natural distribution, then if we are penalizing the learner for abstaining, when X hat looks very much like it could have come from.
Yeah, so what the good part is that if it really looks like it comes from the distribution, then you should predict.
Yeah.
So you won't pay actually, you can just predict. So you won't pay on that. You only pay on abstention. It's a very important part. You're not doing detection. You're just making certain predictions. So you're trying to make your errors low. So even if you have adversarial data and you think you're really good at it, you should just go ahead and predict. Yeah, good question. Yeah.
So is the batch version of this problem the same and still governed by VC dimension?
Yeah, so I will mention that was the original paper by Shafi, Adam Kalai, Omar, and a bunch of people. So they looked at the batch version, but there the train and test both have to be very large, and you get to see the train distribution, and then the test you get to see the unlabeled samples. So it's like a transductive setting, and that also is governed by VC dimension. But this is kind of a little bit more challenging because you have to do it one sample at a time. But it's also not exactly related because you get to see the label after. Yeah. So I'll explain some connections. But even that problem is very interesting in the offline setting. Any other questions? Yeah.
Just trying to unpack the assumptions of the setup. Is that like some intuition as to why this would be a hopeless problem if the adversary could see the sample point and then decide whether to inject / what to inject with that extra information?
Yeah, so I think it's slightly challenging because there's no notion of what the underlying distribution is anymore. Because if it's like, it could select like some part of the distribution and never show it to the learner. So I could never.
Create like a new implicit distribution for the mask.
Yeah, so you'll have to like, but then the adversary has control over the distribution changing over time. Yeah, so it becomes challenging. I mean, it's an interesting thing to think about. I haven't like really worked out that just makes it hard, but it seems like plausibly that it's not gonna work out. Yeah. Yeah, I want to have some notion of IID data. And the model is here like, okay, the adversary can't control if you're thinking about the medical setup, you can't control all the patients that are coming. Once in a while, some patient out of distribution shows up, but it can't change the underlying distribution. Right. So this is why it's the question that comes back, why I don't need to assume a bound on the number of adversarial corruptions, because technically abstentions on adversarial examples are free. So if I abstain on everything, that's okay. As long as if the entire stream was adversarial, I could abstain on everything. That's okay. So the error does not need to scale with the number of adversarial injections, which is nice. But then, of course, you can also argue that if I abstain on anything, I'm not really making any decisions. So the cost of actually abstaining is high in real world applications because you have to get somebody to make that decision for you. So here, it's not the best model. You can assume some cost, but at least in this setting, the way it is that you're making sure that whenever you're predicting, you're actually making good predictions. You're not going to make too many mistakes. So your error does not need to scale as long as you're predicting with some sense of certainty. So why is it challenging? So the adversary can add any number of adversarial injections, as I mentioned, so you don't really know which setting you're in. The learner does not know which examples in the history were injected, so it actually can't compute its own loss because I don't know how many things were actually IID and I abstained on, so I don't really know what that part of my loss is. I can obviously compute my misclassification error, but I can't compute my abstention error. So that makes it challenging to know how well you're doing. The adversary could insert examples that maybe cause us to believe that the function looks differently downstream. It's like really hard in the sequential setting to imagine that the errors are only at that time. And you kind of sort of need to know when you know that the answer is correct to be able to do this. But this is important and goes back to Ramya's question that you're not trying to solve one example adversarial detection, which may be impossible because, I mean, the adversary could just be giving IID samples. As long as you can predict correctly on that example, you don't need to suffer any loss on those examples. Okay, so let me mention a lot of connections. This is has a lot of connections with many other frameworks, and maybe there are more interesting connections that you all might find. So abstention-based learning is not new. It's just not been studied in this adversarial versus like extrapolating between stochastic and adversarial setting in the online classification. In offline classification, it's studied to try to get faster rates. So you can decide to abstain on some part of the distribution and maybe learn faster. And this is the paper that I was mentioning about transductive robust learning, which is in the offline setting. And I'm going to show a slide on this after. And then there's this new paradigm. You can talk to Arsen here who can tell you more about this, which is testable distribution shift, which is also in the offline transductive setting where you can abstain on making any prediction at all if you detect any distribution shift. This will become clear in my next slide. This is the main one that we rely on and build on. And then in the online setting, you can have very strong models. This is this model, this really nice model from 2008, which is know what it knows. And here there's a really strong guarantee. You have to predict always correctly. So you need to really know when you know. And then the guarantees are really bad because they depend on the size of the input space and so forth. So you can't get VC dimension like guarantees here. And again, in online classification, also you can get faster rates by abstaining by doing some expert algorithm, which is faster when you're allowed to abstain as well. But they mostly focus on either assuming that it's fully adversarial or purely stochastic. They don't try to interpolate between the two. Let me just tell you the transductive robust learning setting once, because it's also an interesting setting to study. So if you find this interesting, there are many open problems in this space as well. So here what you have is slightly different. You just get a purely clean label training data. So this is IID and perfect data that you want in your training. And you get some corrupted unlabeled test data, which means that there's a test data that's drawn, and then the adversary can decide any number of points it wants to corrupt on those and can replace them with any other point that the adversary chooses. But you get to see all of them. And before you decide your prediction. So it's transductive in the sense that I get to see all these examples before. And what you want to do here is like you want to decide which of these examples I want to predict on. And you also want to output a classifier that is going to predict when you decide to predict. But you want to minimize something very similar, the incorrect predictions and the incorrect abstentions. So incorrect predictions are basically, if I get the true labels y hat I for each of these points, then how many mistakes do I make when I make a prediction? So this is when I'm making the prediction on the set, I'm just penalizing the loss. And incorrect abstentions is again, how many times did I not predict when xi hat was not corrupted? Okay, so this is the offline setting, and some interesting results are known that if you have an an ERM agnostic ERM learner for this problem, you can solve this task. So if the underlying function class, you can get an ERM oracle in the noisy setting, in the first case agnostic setting, then you can solve this. It also has nice connections to reliable learning, so it is reducible to reliable learning, which is a little bit easier than worst case agnostic learning. So they're like nice connections here. And the questions of computationally tractability of getting algorithms that work are still open. Like there are very few classes that you know computationally tractable algorithms for. But just to make the distinction clear, here you get these samples are usually of the size of the VC dimension. So they're pretty large test data, not like one sample at a time. So with the setting we are looking at is more online, like you have to predict with one sample. Yeah.
Is there like a fundamental separation between the offline problem and the online problem that you described?
Yeah, so I think one interesting thing is that the ERM oracle works for this. I think in what you see as a result, you need to really exploit the structure of the VC class, which is much higher than just knowing how to minimize the loss on the task. So I think it inherently like to identify whether one sample is useful or not. At that point, you need to like really make very different decisions than you're making here. Because here what you can benefit is like if things look similar, you can try to abstain on regions and you can get away with something better. Otherwise, this would not be even possible. And one thing to notice is that you're dividing by 1 over m, not the size of the set. Otherwise, it would be hard. Like if you wanted to like be like dependent on how much the adversary corrupts. So that also becomes a little bit different. But yeah, I don't really know. Maybe there's some like nice reduction that could be done. But I fundamentally think that these are going to be different problems. Yeah, our setup can be thought of as an online version of this. There's also connections to other frameworks. So you can think of this as like trying to extrapolate between online and worst case, right? So you want to do something that's beyond worst case. So I did not make any assumption on the adversary because I allowed as many adversarial corruptions, but there are other settings you could study that. You could assume that the adversary is a smooth adversary, which means the adversary can decide a point, but then the world comes in and smooths that point out. So it can't really be very worst case in that nature. And interestingly, even that adversary, you can get VC dimension-like guarantees. And these are like really nice results starting from 2011. And then Nika and Abhishek and Tim had like follow-up work that really characterizes the complexity of this task. Then you can also make it easier if you can assume that somehow the future sequences that you're going to see are somewhat predictable. Like if there was some predictability in the future, then maybe you could hope to predict them better. So there is some work that assumes that there's some predictability there, or you get some hints about how the future is going to behave. And then there you can also get better guarantees than these worst case guarantees. And then of course, this is related to adversarially robust learning, because you can think of test time attacks, where at test time you're given an adversarial example, or you can think of training time attacks where your training data is corrupted. But here you can think about that because the adversary doesn't know what part of the training data was corrupted or what part of the sequence was corrupted or not. This is trying to handle both test time and training time attacks, because you don't know what training data is clean in the past, and the test data could also be corrupted. And then another interesting connection is to this testable learning. So if you attended Arson's talk at Meet the Fellows, this framework can be viewed as some version of the online version of testable learning. In testable learning, it's just like testing an assumption, whether your data satisfies this assumption. And if the assumption is satisfied, then the algorithm must succeed. So you can think of abstention as just testing whether you're in the distribution or not. And the errors also look pretty similar, like soundness and completeness. So I'm not going to talk much about it, but you should check out his talk to see the connections. And we haven't developed a lot more into this, but there definitely, with the offline setting, there are nice connections. So I don't know in the online setting how to think about this with the results from there. Okay, so now that we know the model and if there are no questions on the model, I can start discussing the algorithms. And I'll try to build it up with the intuition of what you may start to do and then how we came to the algorithm. So I'll think of a very simple class. This is the class which has VC dimension 1, but little store dimension infinite. So you can think of this class of linear thresholds in one dimension. So it's a super simple class. The only parameter is this A, which decides that if the input is larger than A, then it's positive. And if the input is smaller than A, then it's negative. And you're just trying to find this A. Okay, so what the adversary can do here is the adversary can choose a random A. And say, imagine that you've seen so far these examples. This is the part that you know is negative, and this is the part that you know that is positive. So what can the adversary do? The adversary can just inject a random point between the closest seen positive and negative. Right? And the learner doesn't really know where the decision boundary is, right? Because the A was chosen randomly. So the learner must predict it will make a mistake on this with probability half. It won't really know what that label is. And the adversary can keep doing that in a finer grain as it goes on. So this would lead to T/2 mistakes in expectation, because every time I can just, like the adversary can just keep corrupting the points there. But what if you could abstain? You could do something really simple. You know how to predict when you see points on that side, and you know how to predict when you see points on this side because it's realizable. You could just abstain in the middle and not make any prediction. So whenever you're unsure, you just decide to abstain. Okay, so one thing that's really nice about this algorithm is it's never going to make a mistake, right? Because whenever it's unsure, it's just abstaining. So the misclassification error is 0. Now, what about the abstention error? So it's not too hard to see that if you have seen T minus 1 IID examples already, then if you get a new IID example, the probability that it's going to lie between the closest positive and negative will be only 1/T, because it's like the point lying between a random IID example. So this is like a simple exchangeability argument. So you would only see an ID point with 1/T probability. So if you've seen a lot of IID points, the likelihood that you're going to see more IID points in that space is going to reduce. So in the worst case, you can just sum this over all T, and you can get that this is going to be bounded by log T. So you're only going to make log T abstentions on the IID points. So in total, this error, you had 0 misclassification error, and your abstention error is bounded by log T. So you're able to get this nice log T guarantee instead of that T/2 that you would have gotten if you had to make predictions everywhere. Okay, so here it's kind of a trivial algorithm that wherever you're unsure, just don't predict. Okay, so this is abstaining whenever it's uncertain, and this is very well studied, and this is called disagreement-based learning. So it's like abstain on all points in the disagreement region. What does that mean? That the region where there are 2 classifiers that predict everything correctly but disagree on this point. So basically, you don't know whether it's going to be this +1 or a 0, right? So you can, this is often done in active learning and perfect selective classification to use this strategy. But this strategy will always get 0 misclassification error because it's never going to predict unless it's sure that everything predicts correctly. But the abstention error, though it's very well understood for this, is quantified by the star number of this hypothesis class, and I'm not going to describe what star number is. But star number is, again, infinite for most hypothesis class of interest. And for this, the class that I mentioned before, it is bounded. But for even if I go to intervals on a one line, it's infinite. So this is good, but it's not a good strategy. So you kind of cannot go with the strategy that you make no misclassification error. You kind of have to make some misclassification errors. Okay, let me motivate this by considering the example of intervals. Now I'm just going to make the problem slightly harder, and I'm going to put A and B. So now you have to learn 2 parameters instead of 1. The VC dimension of this class is 2. And you're going to be positive only in this region between A and B and negative everywhere else. Okay, so what can happen here? Suppose that the ID distribution has very low mass on the positive part. Okay, so we have only seen negative examples so far. So what would happen if I was a disagreement-based classifier? Like if I was like just deciding that any point that I think I'm not sure about, I should abstain. Then I really have only seen negative points so far. So I would abstain everywhere because the positive window could have lied on any point anywhere. So the disagreement region is basically the entire space. So that's not great because even though I could have just thought that, oh, everything is negative, let me just predict negative instead, I'm going to abstain everywhere. And then I'm going to suffer a really high loss because I could just abstain forever. But what is better is that I should just predict 0. Why is that good? So say if the learner just predicts 0 across this whole boundary, then the misclassification error will no longer be 0 anymore, because if it sees a positive example, it's going to make a mistake. But what happens when it sees a positive example? If it predicted negative and it made an error, means it figured out that this part was positive. So now this reduces to the threshold problem on these two sides. And then you can go again with that abstention strategy where you abstain between negative and positive. So what you did effectively was that you reduced a VC dimension 2 problem by making one mistake into two VC dimension 1 problems. So this problem reduces to 2 thresholds, and then you can use the same idea from before to solve this. And so you will only make one misclassification mistake, but you can trade it off with log T abstentions. Okay, so here this is kind of an indication that you need to make some mistakes, because as long as the mistakes help you with learning, it's better to make that one mistake so in the future you're not going to make any more mistakes. So make mistakes as long as they help with learning. It's a good philosophy in life generally. And this motivates like our algorithm, which is kind of trying to do this idea of figuring out when you make a mistake, when you don't make a mistake, by using properties of VC dimension class, which are, I'll describe higher order versions of this disagreement. But it's going to have a lot of caveats, and you might not be happy with all the assumptions that I'm going to make, but I don't really know how to remove them. So we'll assume that we have actually access to the marginal distribution D. So like assume that it's Gaussian, that we can compute things about this distribution. But then we'll be able to show with just that assumption that there is an algorithm that for any VC class gets the following guarantee: the misclassification error is bounded by D squared log T, and the abstention error is bounded by order D. Okay, this D square is kind of arbitrary. This paper has not been written down, but there's a really nice, cute trick to make this work in D time. The same algorithm, we just have to make the decisions a little more cleverly. I hope Shyam will write this down sometime, but he sent us an email saying that you can make it D log T. So that D square is artificial. Initially, we thought maybe there's a separation, but it's artificial. So you can get the same kind of guarantees that you would have gotten with an IID sequence with this kind of setup. Okay, this also works when F star is adaptively decided, as long as realizability holds. So the adversary could keep changing what F star is, but it has to be consistent with everything that's seen in the past. And you can also allow, because you're making the strong assumption that you have the access to the marginal distribution, you can also allow for no labels when abstaining. So you might not receive the label when you actually abstain. Okay, so let me motivate this algorithm, and it's going to be not that complicated. Like, it's going to use the same kind of ideas that we've already discussed. So you want to predict in a way that, yeah, question.
From when you guys were working on this originally, did you expect to be able to get a bound that's independent of T for both of those simultaneously?
Oh, I don't think so, right? Because you have to pay log T anyway if you do some kind of, yeah. I mean, maybe if you do this some inclusion graph thing. Or,
Before you had the theorem.
oh, I didn't even know if we could get D, VC dimension, when we started. But we were hoping that there should be some way to get this VC dimension like guarantee. So,
And, I mean, do you have any intuition on kind of the creative frontier or design space of the algorithms for this problem? If you can, like how the trade-offs are in your...
Oh yeah, you can trade off these errors. I think you can choose your threshold such that you can put errors more on one side than the other. Yeah, you can do that actually. You can make, I think one-sided is easier. So you, I think, have to make some, okay, it depends whether you get the label or not when you abstain. Because if you don't get the label at all, then you're not going to learn anything. So you can't make it all be abstention. You can't push these errors to abstention.
Okay, you can stop my question if you want. Sorry if I missed something. What conditions did you have on the marginal distribution?
No condition, just I'm assuming I have access to it. This is very strong. Like I can like compute things on that marginal distribution.
Therefore, do you have a strong sense whether the log T is necessary?
I'm not sure it is, but the way that we, yeah, that's a good question. I actually don't know what the bounds are. If like the entire sequence is entirely stochastic, I'm not sure what you would.
So you assume like you know that like p of x.
Yeah. No, only the marginal p of x. Of course, you don't know anything about the label, then the solve task is done. Yeah, yeah. Yeah, but it's a strong assumption because I'm going to actually use it in a very strong way that if I got samples from it, it would be hard to estimate the quantities I want to estimate. So I'm really using access to this distribution. I'll show you some algorithms after that don't use anything, are actually computationally efficient also, but only for very special classes that really need to use the structure. This is here, I'm just like not assuming anything other than VC dimension. So I don't have that much geometric structure other than VC dimension to exploit. So that becomes challenging. There was a question, yeah.
Or actual access?
Oh, so here I mean access to the marginal, not samples. Like I can compute things from the distribution. It's very strong access. Like imagine Gaussian, I know exactly what the moments are. Right, I'm not estimating them. Yeah.
So maybe you already said it, but how does the algorithm scale in the D, the VC dimension?
Oh, it's like, the algorithm, it's not efficient. This one's not going to be efficient because the things that I want to compute are going to be complex to compute for general VC classes.
What's the bound? What do you have?
I just assume you can compute these quantities, but I don't really say so. I mean, if you did brute force, you might take exponential time in the VC dimension.
So then why does it matter whether it's sample access? Like if you don't care about tracking computation, like why does it matter if you have sample access?
Yeah, so that's what I'm saying. I mean, I might not know, right? Like if the adversary chose the distribution and I have no idea what that distribution is, I might not be able to compute those quantities. So I'm going to rely on computing some quantities that depend on the distribution.
Sure, but I'm saying like if you just have sample access to it, if you can just produce like...
Yeah, then I can just take in, yeah, sure. Yeah, but they'll be unrealistic. It'll take like t to the d kind of samples. So I don't want to say that that's at all meaningful to like replace this by a sampling oracle. Yeah.
So if you had assumed the class was finite, you wouldn't need the assumption and you would just get...
Yeah, finite is like, yeah, finite you would anyway work out, right? Because you can just get log h kind of guarantees in that. So here infinite is important. Because I could maintain a net on these things, but in this it's like, because the net could be good on the ID points, but not good on the adversarial points. So I don't know if I'm right or wrong on them.
In the offline setting, do they need to assume marginal access as well, or is there something?
No, so they don't actually. That's why I thought like Ishwar's question that's easy because they can do it as long as, so the algorithm's kind of nice. They just try to use an ERM oracle to separate the adversarial points, the test distribution from the training distribution, and use that to decide when to predict or not. So all they need to do is be able to minimize like how your function class would classify these points. We'll have to use like the structure of the VC class because at one sample I need to decide whether I want to make this prediction or that prediction. Maybe there's a way to improve this, I don't know. Happy to discuss more. But let me tell you the idea. So it's going to be, again, the same, that the goal is you want to predict in a way that mistakes will help you. So you want to estimate when mistakes will help you. And in the interval example, we kind of did this by predicting negative till we made an error, because if we made an error, we would reduce the dimensionality of the problem. So I want to somehow get an estimate of what is the dimensionality of my problem currently. If I can get an estimate of that, then I can see if my prediction will help me reduce my dimensionality, then I can go down. So this should sound like the halving algorithm, if you've heard of it. And this is going to be some version of the halving algorithm for infinite VC classes, dimension classes. So this is just like the interval going to a threshold. So VC dimension 2 to VC dimension 1. So what we're going to use is this idea of shattering. So this is how VC classes are defined, right? Like how the higher the VC class is, like the more points you can shatter. What I mean by shattering is that shattering is a set of size k set to be shattered by some function class if it's possible to create all possible labelings of that set using your function class. So that really means that with those many points, you can really not understand the complexity of the function class because you could get any possible labelings from your class. And the VC dimension is the highest, the largest size of the set that can be shattered, and nothing more can be shattered beyond that. So these are like canonical examples of shattering points, like how many points, what the size of the VC dimension is. Okay, so what we're going to try to do is estimate how uncertain you are by estimating what is the probability of you being able to shatter the function class. So if you've like really shattered at some level, means you really understand that function class at that level of complexity. And if your shattering probability is low, you don't really know. So you can compute these higher order disagreement-based quantities that are from Steve's paper, actually used in all active learning setups, not in this setting, but it's kind of all related because you're trying to estimate uncertainty of what you don't know. So you can define this level k. At any level k, you can define this shattering probability with respect to a distribution, is that you can sample k random points from that distribution and see if the function class shatters them or not. So it's kind of estimating for that distribution of points, this function class, how complicated that function class is. Right? So if your shattering probability is really high, that means that on this distribution, all these points could have been labeled anyway. So you need to like get label information to actually understand what's going on. And you can think of row 1. If you just picked one point, it can be shattered, means that there's two functions that can give different labels to that point. So that's just the disagreement region. And row k is always greater than row k plus 1, because you're just taking more points and deciding whether they're getting shattered or not. And row d plus 1 is 0, because no d plus 1 points can be shattered. So there is some sequence of reducing values. So this is 0. This is the probability of, increase. Yeah. So row 1 will be the highest quantity, and then going down, you'll get to 0 at row d plus 1. Okay, so this is kind of the quantity that we'll use to decide to predict. And the algorithm will be very similar to halving. So you're going to start with the current level being k equal to d, because you don't know anything about the class right now. So you'll go to the highest level of uncertainty. To make a prediction on a new point, what are you going to do is you're going to compute the shattering probabilities, assuming the two quantities, whether the label, if I label this 0, how much is my shattering probability going to change? And if I label it 1, how much is my shattering probability going to change? And if both quantities are large, means that this point is not going to give me much information. I'm just going to abstain. Otherwise, I'll predict according to the larger one. Why would I predict according to the larger one? Because if I make a mistake, I go into the smaller world. Okay, so these are the actual bounds that you use. You have to use it relative to what the level above is to get the bounds correctly. And so if both quantities are small, and the small is like really small, that's why this estimation is annoying. T to the minus k. So if I'm at level k, I need to go down to on the same level. I'll stay for a while till that quantity becomes really small, and then I'll just go down a level. That means I've just saturated this level. I really understand my class at this level. I should go down. And then you can, after you get the label, you can just update your version space to whatever new version space there is. And once you're at level 0, then you can just abstain on any point in the disagreement region and predict correctly wherever. In some cases, you might never reach level 0. So if your ID distribution was all negatives in that interval example, there is no positive point. So you're never going to get to the point, like, because everything is in the disagreement region. But at level 2, it is not. So you'll just stay stuck at that level. Okay, so why does this work? I'll tell you why. For ID points, I need to show two things, right? I need to show that I don't abstain too much. So I need to somehow say that for ID points, this cannot be both large. And I should be able to say that this algorithm will, every time it makes a mistake, it should do some improvement, so my mistakes are bounded. The second part is easy, because every time I'm gonna choose this quantity such that I'm gonna predict the max. And if I'm wrong, then I go to the min world. And the min world is a constant times better in my quantity. So eventually, I will only make like some log of this threshold number of mistakes till I get to this quantity. And then I'll have at most d levels. So that's where this d square shows up. But you can improve that. You don't need to actually do this. You can make progress on many levels simultaneously. And there's a clever way to do this, so that you only pay for d log t mistakes. So this is similar to halving for finite size, but we have to do it at each level to get to understand the uncertainty of our space. And now it's not too hard to see why this is going to be not true with high probability for ID points. So this is the kind of lemma. It's a very simple Markov inequality using the properties of shattering that we show. Basically, this is saying that the probability of both the quantities being large is bounded by the ratio of what the quantity is on the level above you and the level below you. And the intuition is the following. If you take k ID points, if they are shattered by both, which means both quantities are large, then that means I can take this point and these k plus 1 points will be shattered. So which means that the quantity in the level above should have been large. But I already assumed that I'm going down the levels, so I would have reduced that quantity. So it's not possible for an ID point to satisfy this, which basically means that the ID points have to give us some information at every point. So since for ID points, this can't happen too often, there's like some ratio with what you're paying. And then that's why we have to keep this ratio small enough to be like 1 over t, so that we can only have like a constant number of mistakes. So this is basically the idea. It's actually like not like 4 or 5 lines to just prove this. Is not using anything sophisticated other than the definition of shattering. So that combining the two, you get these guarantees. It's the limitations. I'm going to say limitations because it's very limited, and this is not what I desired or wanted to prove when I started out. It requires access to exact marginal distribution. Now you see that I had to compute this shattering probability. That seems like very hard to compute efficiently, or like even I needed to compute to t to the minus k accuracy, which is like t to the minus d accuracy, which I cannot feasibly do given my sequence so far. That would be nice, like if I could just use the data I already had to compute these quantities. And then checking the shattering can be computationally inefficient. Even if I could deal with the sample complexity, I don't know if the computationally this would be possible. However, when I started out, my goal was to even show that you can get VC-like guarantees with this adversary that can like put as many corruptions as possible. So I think it's good to know that at least it is VC dimension is the right control of this quantity. It'd be great to get progress on any of these questions to get rid of these assumptions. Yeah.
Would you use the previous sequence to estimate this quantity? Because some of those points could be.
Yeah, so what would you need? Like, okay, so if assume everything was IID, then you could do some leave out K estimation, like drop K points and evaluate like what the shattering is with respect to the rest of the function class. And then I would have to do some robust version of this with these quantities. But yeah, it's not clear. I could do something with like when I made mistakes, when I didn't make mistakes, try to use that. But I really don't know how you would do that. It seems like a very hard problem. Yeah, maybe some SOS. I was thinking like some SOS style thing that can predict what the errors are and assuming some fraction. So if there are too many errors, then maybe I don't need to compute with very high confidence. If there are few errors, I might, something like that, some trade-off might exist. I'm not sure. Yeah, you can probably try this better than I can. So that was the goal. The goal I started with is just show VC-like guarantees, but it would be nice to remove this. In some cases, we can. This is not going to be very satisfying, but for VC dimension 1, any VC dimension 1 class, you can get this without access to the marginal distribution. So you don't need to know anything about the marginal distribution. You can get guarantees, but they're like significantly worse. You get square root t kind of regret instead of like just like log t that we were getting before. And this is much worse than the known marginal case, but at least in this, it's possible, but you have to really use the structure of VC dimension 1 class. There's this really nice result by Shai Ben David that shows that VC1 classes can be thought of as paths on some tree, and we really use that tree structure to be able to get the uncertainty estimates. Another thing that's like more reasonable maybe is like for axis-aligned rectangles in any dimension D, we can also get an algorithm. And that again obviously suffers from this scaling of square root t. Again, I can't get the best optimal bounds, but it again does not need to know anything about the marginal distribution. And this algorithm is kind of nice. I'll describe it in the next slide. It's kind of intuitive what the algorithm is doing. So maybe there's some way to extend these ideas, but it definitely exploits the structure of axis-aligned rectangles, which is like that axis-aligned rectangles, you know exactly all the dimension directions that you need to solve the problem in. So you can kind of split a VC dimension D thing into like sub-problems that are lower VC dimension. So it really exploits that, and I don't really know how to extend beyond this kind of structure. But let me just explain this algorithm in the last 10 minutes I have. Okay, so I'm calling it the rectangle learner. But what is an axis-aligned rectangle? I'll take a very simple setting. One of the endpoints is always at the origin. And what I'm trying to find is like, which is the bounding box here that decides whether I'm going to be negative or positive. So anything inside that box is positive. Everything outside is negative. And let's just say that this is two-dimensional. So all I need to find is like one point that defines my function class, which has two variables. So this is a VC dimension 2 class. Okay, so suppose that these are the points that you've seen so far. You can do a similar thing that we did before, that in the interval case, you know that this area will always be positive because it can't be negative because your class is realizable. And this area will be negative too. Anything outside what you've seen will be negative. So these things you can be sure on predicting. So whenever you see this, you can just predict correctly whenever you see a point there. The issue is that you don't know what to do when you're in this region, because it could be positive or negative. So you have to make a decision somehow what you're going to do in this space. So what we do here is this idea that to make a prediction on a new point that you see, if it's here, I'm just repeating this. If it's not in the disagreement region, you can predict according to the consistent label. But if it is here, what you do is you kind of try to see, what points. If I project this problem down into like the different directions, does this point seem more negative or more positive? What does that mean? So say I projected this point down here in this dimension and in this dimension. So what's going to happen here is that according to these, if I think of this as an interval problem, just like a one VC dimension, one threshold problem, then this point, when it's projected down, is negative. So this is on the other side of that. So this point is kind of voting that this should be negative if I looked at only this dimension. And similarly, if I point it here, this point is voting that this should be negative. So we basically count all these votes, that what are the points that are voting to say that this is negative or seems negative. And these are votes that you count. And these votes, if there are sufficiently many votes, if there's like alpha number of votes, I'm going to predict negative, else I'll abstain. Because otherwise, I really don't have any information. Nothing is telling me whether it's positive or negative. So I'm going to abstain. And then I can just update and repeat this process. It's very efficient to implement, but it really uses that I can break this problem down into like these VC1 directions. And the proof overview, I'm going to just give a high-level idea. So make no mistakes on positive points, because you're never predicting positive when you're unsure. You're either predicting negative or you're abstaining. So no points. And every time you make a mistake, what's going to happen is that some point witnessed and said that this should have been negative, but I made a mistake in that direction. So that point cannot vote for any other points in the future. So each point can only vote for two directions. And there are only two t points and two directions for each point. So in each point, when I make a mistake, I remove alpha of them. So I can only have two t over alpha mistakes that I'm going to make, because then there'll be nothing left to vote for. And the interesting thing is that the adversary cannot fool us on new IID examples. And the idea is pretty similar to the exchangeability argument, because you can do that on each axis. And negative points, you cannot have many points that lie exactly between or on the other side of a negative point. So you won't have too much abstention error. And the way the trade-off goes is this is 1 over alpha and this is alpha. You have to choose alpha to be square root t. And that's where you have to kind of trade this off. The trade-off is really bad. In the other case, when you have access to distribution, actually, the interesting thing is the trade-off is 1 over alpha here, but exponentially small here. So you can trade off in an interesting way. Here, you kind of have to pay for both errors somewhat equally. OK, so I'm going to end by just discussing some open questions, because I really don't understand much in this space. What can you do with general VC classes without this distribution access? All the known results really exploit the structural properties. I really exploited that this was a rectangle. But some kind of voting mechanism would be cool if you could get some estimate of uncertainty of a point. Maybe we can try to get some heuristics for more complicated classes and try this out to see if we can get some uncertainty estimates. Beyond realizability, of course, I was assuming strongly realizability because it was all on version classes. And once I get noise, it's a little bit hard to deal with. Maybe random classification noise you could still handle because you could still get some approximate guarantees. But I don't know how you could handle any other kind of noise. So try to see what noisy setups do here. And then binary classification is very simplified. Maybe multi-class, partial concept class, or regression would be a more interesting setting to study. And what the complexity of this problem is in these is not clear. The reason for technically, the reason why we can hold multi-class and partial concept is this doesn't use uniform convergence explicitly, because it's actually computing all these shattering things. So maybe it can extend to those settings. And then computationally efficient algorithms, of course, unless these algorithms are computationally efficient, they're of no use. So it'd be interesting to understand, are there actually trade-offs that you can't get computationally efficient algorithms? That if you want computationally efficient algorithms, maybe you have to pay worse regret, or it's just not possible. So I don't really know what the computational aspects of these questions are. And then I think over time, similar setups have been studied and very, because the underlying problem is kind of simple. You kind of want to understand whether this point is good or bad. And this kind of shows up in alignment and many problems that you care about. So there have been connections to a lot of different problems and techniques. I'm already mentioning testable learning, conformal prediction, SOS-style robustness, but these ideas kind of show up everywhere. So there might be nice connections or some way to really summarize this whole attempt to understand the uncertainty of points using techniques from each other. So we used with Arsen and a couple of people from UT Austin, we tried to use some kind of SOS, it's not exactly SOS style, but some kind of outlier removal techniques to get better algorithms in the offline setting. But I don't know how these would ever extend to the online setting. So it'd be interesting to see if some techniques like that help. And that's all I have. So I'm happy to take any questions. Thank you so much for your time.
for questions if people. There was a lot of chat.
So can I just ask about the finite case again? As you said, it's somehow easy. Is it easy because you just never have to abstain in that setting and you can just do halving?
In which case?
In the case when you have finite.
Yeah, you can just do halving.
So you don't have to abstain that.
Yeah.
And there's something wrong about me thinking about a BC class with a known distribution. I can create a net and then
You can create a net, but the net is only supposed to be good on your IID points. But you have to make a decision on a point that is not IID, right? So that
I
net.
cannot just run halving on that. Right?
No, because then the point that you get, maybe the halving algorithm is going to predict something, but that the guarantee of the halving, the net being good is only on IID points. So it might not be good on that point at all for prediction purposes. Yeah, so I want to come up with like a neat example to show this, but I've not been able to like really nail it down. It doesn't work out. That's a good question.
I have a question.
Yeah.
So this choice of alpha, did you think about like you could possibly choose it sequentially?
Yeah, so adaptive alpha would be cool. Yeah, you can probably try to optimize a little bit, but I don't think it's going to get you away from the square root t. But it's probably possible, and maybe you can, I don't know, like you can make like, these are worst case assumptions, like you can assume the adversary is not that bad, and then you can maybe get improvements on these algorithms. Or you could estimate that, try to estimate how bad your distribution was so far, and rapidly change alpha. Yeah, it's possible.
Yeah. First of all, thanks a lot for the talk. So you had this very simple examples that I enjoyed a lot. You had this threshold, for instance, and then you had this clean method. But so that's not very robust to say label noises. So in such a simple setting, would you have an idea what you could do if there would be a bit of label noises?
Yeah, so in I think active learning or other methods, they try to create like error bounds around the shattering. So like you keep more classes than you need to keep. If the noise is benign enough, that would still work. That I'm not going to be so aggressive in like deciding whether it's predicting 1 or 0, but like allow some error bar. So I think something like that would work, but like very benign noise. Like if the noise is hard, then yeah, these techniques would break. I think I'm not sure if there's a good way to extend these. So yeah, I mean, it's not very satisfying, but you're kind of trying to understand whether something is in distribution or not distribution. And the benefit is that there's like a really true simple classifier that can actually tell you to distinguish between this. And then if there's noise, I'm not sure how easy that would be. And it's in the agnostic noise, I'm not even sure what guarantee you're trying to achieve. Like what would you want to compete against all the times you predict? What is the best loss that you could have gotten? I'm not sure what the right modeling would be in that space. But it would be interesting to understand, at least like benign noise models, that it should not be so brittle to noise. Like the voting thing that I mentioned would like be super brittle to noise. So it's going to count a lot of things, anything noisy. But maybe you can scale it by some factor and it's fine.
Maybe we have time for one more question. Anyway.
Yeah. So I guess this is a really interesting setting. So we've looked at not like the adversarial setting at all, but like there's like there's two different things. One is the auto labeling, where like you have like unlabeled data and you're trying to like get as many labels as possible, like automatically, like so classified, but the class might not even like it might not be a realizable class, but you're allowed to query labels. So you want to kind of maximize the number of points that are automatically labeled, subject to reliability guarantee that among the automatically labeled point, you cannot have more than 5% of it in error, let's say.
Oh,
so
okay.
So in there, again, what we do is iterative selective classification. So maybe like I think there might
maybe some ideas would. Yeah, because the algorithm that we use is kind of actually an algorithm that exists in some active learning setup, but it was never used to analyze online learning algorithms. So I think there's like very deep connections between all of this. I don't know why we needed all this higher shattering. We kind of really needed it for this. Maybe, in other most problems, you can get away with disagreement. You don't even need to do anything more sophisticated.
Like from the similar like disagreement agent thing, but we actually wanted something that we can implement and
yeah.
Realize that there are these kind of uncertainty quantification stuff we could do and could but
I should add uncertainty quantification here. It'd be nice to see if you can get some guarantees like that.
But the other line we were looking at is like more of like the OD, like you're actually trying to figure out what is like the outlier, like that's more in the online setting, there like if you say like let's say I don't know, is when you get the label back to know whether it was adverse, like
Oh,
actually.
you actually get the, yeah. So I don't know if we start getting the feedback, I think it'll become easier.
So there again, like I think there are like again, like I think if you restrict how many feedback you get,
Then you will have, yeah. Yeah, you can also assign like cost of like abstaining, and I think there's like another paper by Theodoros that like puts a queuing system also. Like the feedback you get is much later on those labels, so there could be like a lot of interesting settings you can play around. Yeah, play around with.
So maybe I'm gonna just close it here and leave
Yeah.
the chat off.
Thank you.
So next talk at 2:15.